Hello my dear students, welcome back to the second lecture series of feedback amplifiers, which is the third module in analog electronic circuits. I'm Bhaskar, working as assistant professor in the Department of Electronics and Communication Engineering, SJBIT Institute of Technology. So before we move on to the articles of today's discussion or the learning objectives, we'll try to recall the things that we discussed in the last class, because recalling is always very important for us. Fine. So in the very beginning, what is basically a feedback? We took an analogy as well to understand it, and we got to know that feedback is something where you try to take the part of the output and feed it back to the input. Correct. And later on, we also understood what are the two different types of feedback. One is called the positive feedback, other one is called the negative feedback. And then we wrote the general structure of a feedback, and we tried to derive the expression for the closed loop gain, AF. We got it as A divided by 1 plus A beta. And later on, we also understood why do we have to use a negative feedback. Correct? What are the advantages of it? So we got to, know that there are many multifold advantages of a negative feedback, like the bandwidth increases, the gain gets stabilized, the input impedance increases, the output impedance reduces, and what else? The distortion is going to come down. It's basically a nonlinear distortion that we were talking about. And then what else? The noise is also going to come down. And we also had the mathematical feel of all these advantages. We mathematically got to know that yes, there are these advantages available as far as the negative feedback usage is concerned. Correct? So these were all the things that we discussed in the last class. Now we shall move on to today's discussion topics. Number one is topologies of feedback. We'll also be talking on the first two different types of topologies. One is shunt series and shunt feedback amplifiers. These are the learning objectives. Number one, what are the different feedback topologies that we have got? How do we identify the given topology as so and so, or the given feedback amplifier as so and so topology? We'll also get to know things on shunt series as well as the shunt feedback amplifiers. So before we get into the topologies, I think we must be in a position to get to know what are the basic types of amplifiers available. Anybody can name those? Probably we are very familiar with what is called as a voltage amplifier, and we always think that that is the only kind of amplifier available, but we are wrong. The first type is anyways a voltage amplifier, but other than this, we also have got something called as a current amplifier. Then trans resistance amplifier. Probably none of us would have heard about this. Trans resistance amplifier. And lastly, the trans conductance amplifier. Now let's look into the simple block diagram of it, like how this amplifier is going to look like. A voltage amplifier is very simple to realize, or very simple to imagine. We apply the input voltage and we expect an output voltage, correct? And the box which is connected between the input and output, we call it as an amplifier. We know how to represent the gain of it. What is it? It's basically AV, which is V0 divided by Vn, correct? It's V0 divided by Vn. So in voltage amplifier, both the input and output quantities are voltages. And what we get as a gain is basically a voltage gain. Hence it is called as a voltage amplifier. Okay. Now let's see the current amplifier. How does it look like? A current amplifier is looking like this. Very obvious that both the input and output quantities must be a current quantity. Why? Because finally the gain, when I find, it should have only the current values, I0 by II. So hence the name current amplifier to it. Then we have got something called as a trans resistance amplifier. So in trans resistance, how do we represent or write a resistance? Resistance is nothing but V by I, correct? So if I want to represent the gain of this block, which we are calling it as a trans resistance amplifier, we write it as V0 by II. So the input will be a current quantity and the output will be a voltage quantity. Hence it is called as a trans resistance amplifier. And lastly, we have got something called as a trans conductance, which is inverse of resistance. So at the input you will have a voltage quantity and at the output you will have a current quantity. And the gain is I0 divided by Vi. Remember, in the last two amplifiers, we are using the word trans because we are trying to relate the output voltage or current by input current or voltage respectively. In the third case, trans resistance amplifier, output voltage versus the input current, correct? output voltage versus input current. So two different quantities are taken which are totally different, voltage as well as the current. So hence the word trans comes in the picture here. So these are the basic four different types of amplifiers. Remember, when we try to arrive at the topologies, we are going to use these basic amplifiers and try to connect the amplifier, the feedback network. So based on that, we are going to say that it is so and so topology. Okay. So it is these four basic amplifiers which plays a major role, but beyond it, we have negative amplifier which gives us the advantage. So what we'll do now is we'll quickly try to understand as to how we arrive at the topologies. Okay. So what I'll do is I'll take a simple the structure that we used in the previous lecture series. We have something called as a source. Then this gets applied to the amplifier. Let's call it as A. And then we get an output. I will not indicate the load here because it is very obvious that a load will always be there because we have to use it for some application. And then we get this feedback network. So what will the feedback network consist of? It will consist of beta, correct? And then that goes back to the input side. So from the basic definition, what we say, a part of the output which is taken out from this point, or I can use the word sampled. A part of the output is sampled and fed back to the input side, and at the input side it gets what we call it as mixed up. So we can call this as mixer. So we have arrived at two different terminologies. Now one is called as a sampler, other one is called as a mixer. Let me call it as a sampler. Okay. So what a sampler will do, it will take a part of the output and feed it back to the input side. It is going to take a part of the output. Feedback network will feed it back to the input side, and mixer will mix it. In what way it is going to mix, or in what way the sampling is taken or done, it depends on what quantity we are interested in. Okay. So let me look at the four different amplifiers that we have. The four different amplifiers, let me write down: a voltage amplifier, a current amplifier. Let me write these as amplifiers. Then what do you have? Trans resistance amplifier and trans conductance amplifier. So let me make a tabular column indicating what are all present at the input and output of it. So let us say this is input, or let me start with an output because I first sample it and then mix it. First is output, second one is input. Why did I write like this? Because in feedback, first sampling comes in the picture and then gets mixed up. Without the sampled value, how can you mix anything? Correct. There cannot be anything in the feedback without sampling. So I'm writing the output first. Okay. And remember, when I give the names to topologies, the same rule is followed. The first word comes from the output side, the second word comes from the input side. Okay. So let us write the input and output quantities that are available here quickly. Oh, fine. You're good to go now. So can you recall from the previous slide as to, in case of voltage amplifier, what will be the output? I want a quick answer on this. Yeah, it is output voltage. And what will be the input? It will be a voltage again. Let me call it as Vn. Current amplifier. What will be the output? It will be a current quantity. And what will be the input? It will be a current quantity again. Trans resistance. It's very simple to remember. When I say resistance, you say V by I. And V is relevant to the output and I is relevant to the input in this case because it's an amplifier and we are defining the gain. So it will be V0 and In. Very simple to remember. Transconductance is reverse of resistance. So it is I0 divided by Vn. I0 divided by Vn. Let me erase this and write the correct one. I0 divided by Vn. Oh. So I hope till here things are all very clear to you. I think we are going in the right way. This is output and this is Vn. Now let us consider one kind of basic amplifier. Let us say it is a voltage amplifier. Let's say Now looking at this tabular column, one can obviously say what is the quantity that I am sampling at the output. It will be a voltage value. I want to ask you a very simple question. If I want to take a part of the output, what will I normally do? I will take it always across, correct? Supposingly, if I have an output terminal, let us say this is a output terminal. We are considering a two-port network. Here in the block diagram, even though we have written a single port, but normally all amplifiers are two-port networks. So I'll consider a two-port here. Two lines indicates two-port network. Okay. So this is where the output of the amplifier is coming. I want to take a part of the output. What will I do? Can I connect it in series? I can never do that. Voltages are always taken across, correct? So I'll be trying to take it across this and feed it back to the input side like this. This goes to the feedback network. So what I'm trying to convince you people here is, when I want to sample an output, I'll always be taking it across. When I want to sample an output, I'll always be taking it across. When I want to sample a current, I'll take it in series. So let me write that. All very basic things which all of us know, but I'm trying to just put it in the right way here, that's all. So when I want to sample, let me write it as sample here. When I want to sample a voltage, I'll take it in shunt or parallel. Let me write it as shunt. When I want to sample a current, what will I do? I'll connect it in series. Now I want to mix up at the input side. Now the voltage is being sampled and the feedback network will take it towards the input side. Now what should I do at the input side? Remember, we are talking about a voltage amplifier, and the quantity that has to get into the amplifier is again a voltage. So while mixing it, I should mix with the source signal. And when mixing happens, as far as the voltage is concerned, remember, I cannot connect it in parallel. It will be nonsense if I connect it in parallel, because two voltage sources connected in parallel will give you what we know, correct? So what will I do? What is it I'm going to do? I'll connect it in. Any good answer? In series. So I'll say, as far as mixing is concerned, let me write mixing here. Mixing voltage value will be what? Series. When it comes to current, I'll have to connect it in shunt. If you remember, or if you understand these two rules that I've written here for sampling as well as mixing, then we are good to go with the topologies. We can understand, or we can now list out the topologies that we have got as far as the feedback amplifier is concerned. Okay, are we good to go? Can we move ahead now, or do you really want me to write how actually the block diagram will look like? We shall see it, don't worry. Once you are through with all these things, if you can recall and if you can remember and understand these points what I've told, then it is very easy for us to write the topologies and even understand it as well. Okay, now I think it's good time for us to list out the topologies. The four basic topologies. First one is called as a series shunt. The second one is called as a shunt series. Please have a look at these words. Shunt series feedback. The third one is series. Let us start from the beginning. Shunt, series shunt. Why do I use the word series shunt? Let's go back to the previous slide and see what is there in that. We are calling this as a series shunt. Let me write down that. We are calling it as a series shunt. Why do we have to call this as a series shunt?